Hello everyone, thank you very much for having me this evening and turning up. I'm hoping you can all see my screen. It should look like a presentation. Yeah, brilliant, okay. Brill. Okay, so I'm Polly. My supervisors are Professor Cathy Holt and Dr. Phil Anderson, and I'm based at Cardiff University Musculoskeletal Biomechanics Research Facility. So I'm just going to do a little bit of background of how I got here. So as Stephen said, I did a mechanical engineering apprenticeship with the Ministry of Defence. And after that, I worked in Barrow-in-Furness as the desk officer for ship systems for future submarines. And I then resigned and decided to do my undergraduate degree at Cardiff University before going on and doing starting a PhD in medical engineering. And I've just started my third year. I'm about 3 months into my third year, and it's a 4-year PhD. So I'm trying to do device development. It's quite practical, and it's kind of proof of concept kind of thing. So a little bit of background on the technique I'm using first. So the main technique I'm using is acoustic emission. It's a non-destructive testing technique. It passively monitors for ultrasonic shock waves, which are released from damage or defects when a material is loaded or stressed in any way. And you can use sensors to monitor these in static structures like bridges or tunnels, or more dynamic systems like aerospace structures. So it's a well-known structural health monitoring technique, and is used widely on the bridges and aircrafts part of my title. So that little bit of background will help with what I did in my undergraduate work. So I did a couple of projects as an undergraduate. I was quite lucky to do some research projects. One of those was in the summer. I worked for 8 weeks on testing how acoustic emission attenuates through soft tissue. And you can't just test on human soft tissue. It's quite difficult to just get hold of it and store it safely and everything. So we used a tissue phantom. So the piece of metal that I'm bandaging, the soft white squishy bit, is a tissue phantom. It behaves acoustically like skin or muscle or fat. So it's a good estimate when trying to understand how ultrasound moves through skin or soft tissue. So I attached the sensors to the skin, and we put a acoustic emission burst, a HN source, through the metal and detected it. And what I was trying to show was that tissue thickness doesn't affect how the sound travels to the sensor. And that worked quite well. We showed over the summer that various different thicknesses of tissue phantom don't seem to make a difference. So you can detect acoustic emission through 1 millimeter of skin or soft tissue, all the way up to 20 millimeters of skin and soft tissue. So quite a lot of fat or muscle or tissue around a joint. And this really forms the basis of my PhD project, of kind of showing that it's possible to detect these acoustic emissions through skin and soft tissue. And for my dissertation, I did a very similar thing with acoustic emission, but on dental implants. So here I'm implanting proper dental implants that would be put into people, but into sawbone, which is a tissue phantom of bone, and detecting the acoustic emission that comes out of those when you're tightening it. So when you're putting a screw into bone, it will crush down and you can hear the cracking. And then I pulled them out to see if there was a link between implant stability and the noises that it made whilst being implanted. And there was, we've kind of parked that work for now, but hopefully we'll be able to pick it up again in the future and create a device that dentists can use when putting dental implants into people's jawbones. That would be the goal, hopefully. But on to my PhD. So what am I trying to do? I'm trying to develop a patch or a wearable device that can detect knee osteoarthritis. And this would be something that clinicians could use for detecting and monitoring osteoarthritis. So the picture on the right is a concept of what it might look like. It equally might not look like this, but this is one idea. But why would we want to do this? Why is this important? So osteoarthritis affects a lot of people in the UK, 8.75 million people roughly. and costs a lot of money. And this isn't just in treatment, this is in lost working days. So people who are too disabled or debilitated by osteoarthritis to go into work for whatever reason. Current detection methods are expensive and also subjective. It kind of depends on your doctor, how and when your osteoarthritis is diagnosed and what sort of treatment you end up having. But if you can detect it early, if you can detect it when someone doesn't have very damaged knees or cartilage like it looks like on the right-hand side of the slide, you can put interventions in place. So this would be things like weight management and trying to keep that person active, because it helps to slow and manage the osteoarthritis as it's developing. So that's why we need to do it. How are we going to do it? So as I said before, I'm using acoustic emission. So when something's loaded, an elastic wave is released from any damage and it travels through a material and can be detected by an acoustic emission sensor. Now, acoustic emission has been shown to occur within the body from knee and hip replacements, also from bone screws, and if you're plating a fracture, you can hear it then as well. And it has been shown as well in what are called activities of daily living, so things you might do during the day, on people with intact knees, so people who haven't had a knee replacement, it's just their natural knee. And yeah, that's what I'm trying to do, trying to use the acoustic emission to hear this osteoarthritis inside their knee. I'm going to go into a bit more detail on how I'm trying to do this. So these are the different things that I'm trying to do on my PhD. So I'm having to develop the electronics, I'm developing the patch to go with it, I'm learning the lab that I work in as well, and then integrating all of this together, all the data processing, and then reading, writing, and dissemination and teaching and stuff along the side of my PhD. So I'll go through this kind of step by step. So along the bottom, what you can see are different acoustic emission systems. So what I'm trying to do is go from the big device that's on the left-hand side all the way through to something that's quite small and quite light. So if you just look at the top acoustic emission system that's on the left-hand side, that weighs about 3.5 kilos, so quite heavy to be lugging around during activities of daily living and seeing if you can hear noises with. It's very good, but it's quite heavy. And the work I've done so far has gone down onto a picoscope, which is just a type of oscilloscope. And again, this is not too heavy. This is about 500 grams, but it's constrained to that it needs to be connected to the mains. It needs power, needs connecting to a laptop. So all of these wires would have to move with the person whilst you're listening to their knees, with a sensor attached to their knee. And this is dangerous. You can't really have people walking around with lots of wires everywhere. It's a trip hazard, and you're limited to what sort of movements you can do. So generally static sort of movements of either sit, stand, sit, or squats, or leg raises, things like that, things people could do from the chair. What I would like to do is be able to listen to people's knees whilst they're moving, so using dynamic activities. So walking, I would like to be able to do stair climbing as well. So we have some instrumented stairs in our lab. I'll show you some of those later. It's quite interesting. So what I want to do is be able to capture the acoustic emission signal onto something such as a Teensy, which is the picture on the right hand side, or an Arduino or something like that, but I'm aiming for a Teensy, and they weigh about 5 grams. So it's quite a lot lighter than the picoscope as the next one. But it's developing the software to go on it and the hardware around it to filter and amplify and store the signal that's coming off the knees, make a device that's safe to be worn on the body, so there's no risk of people being electrocuted or getting burns or anything from the device heating up. And it needs to run and store data, so be powered and write to a memory card for about 3 hours. That's how long a motion capture session typically takes for us in our lab. So that's the goal, is to get down to something quite light and quite wearable, and hopefully it won't interfere with the participants' movement too much. Okay, so the next kind of line of work I'm trying to do is develop the patch that will be worn. And one of the big questions is kind of how are we going to stick this sensor down onto somebody? When you're dealing with bridges or aircraft, they don't tend to move that much. You can kind of stick the sensor on and leave it there and you don't have to worry about moving it. Whereas the soft tissue around your knee and around your joints will slide quite a lot. It stretches as you're moving. So we need to try and make sure that the sensor is adhered nicely to the skin or tissue around the knee and can hear the sound that's coming off the knee nice and cleanly. So ways that you do this with metals or other composites would be silicone grease or maybe super glue. There's other ways as well, but we can't really go around sticking silicone grease and super glue on the human body. So I've had to have a look at some different silicones. I've also tried things like Vaseline. I tried wound glue, like the kind of glue that you glue head wounds together with, and that didn't work so well, but we gave it a go. I'm trying to decide how to adhere it to a patient or a participant without it hurting their skin for those 3 hours. So one thing I've tried is cutting up an ECG pad. So along the bottom, that's just an ECG pad that would be stuck to you to have an ECG. So the crocodile clips go onto it, and then casting silicone into the mold and then sticking the sensor down into it to see if that would work. The work's ongoing on this, so hopefully we'll get some nice results out of this soon. But yeah, this is the other line of work. If this goes to market, then we'll work with a like a patch company or a plaster design company to try and get a really good system. So I also have to learn all the labs. So this is one of our labs in the Musculoskeletal Biomechanics Research Facility. It's a fairly new facility in the School of Engineering. And we have 3 large labs. So this is our clinical lab that you can see at the bottom of the screen. We also have a teaching lab, which is essentially the same, but on the other side of the wall, and a fluoroscopy lab. So fluoroscopy is high-speed video X-rays. So we can actually see the bones moving whilst also doing motion capture. So this is a motion capture lab. There's cameras all the way around the room. So you can see some here in the oval shape, and there's some around this side as well. And this is very much like, I don't know if you've seen things like Lord of the Rings, where there's the motion capture markers on people and they record how people are moving and then animate over the top of it. It's that. But we don't animate people. We just see how they're moving, and we're trying to see if they're moving in a normal way, or if they're moving in a way that might suggest that they have some sort of pathology going on. As well as the motion capture cameras, we have an instrumented walkway. So there are force plates in the floor, and these allow us to see how people's force changes as they're moving in their normal gait cycle. And this can tell us things about how they're moving as well. So the clinical lab is quite rigid in how it's set up. We can't really move the cameras or change the layout because it's been certified that it gives out data to a particular standard. And it's used in making clinical decisions for children who will need surgery for cerebral palsy. So we need it to be very consistent and very reliable. And the NHS clinic come in and can assess these children and help advise the surgeons on when might be a good time to perform surgery if it's required. So I tend to use the teaching lab. All of our undergraduate projects run in the teaching lab as well. And we can take the cameras off the wall and move things around, and it's much, much more of a flexible space, which is quite nice. So the next couple of slides are going to show you kind of what I will be doing with the markers and stuff. So on the left-hand side is an example marker layout. So the bright white or silver balls are markers. So these are what the cameras that were all around the room see and track, and they are attached to anatomical landmarks and also other other features on the body as well. And the little black boxes you can see are electromyography boxes. They monitor muscle activation. So when you're walking, if you're healthy, your muscles work in pairs and it allows you to move normally. Someone who has osteoarthritis or another pathology, you might see that their muscles don't activate at the right time, or they don't activate together in pairs. So the next picture shows you what the cameras see. So they see these sets of markers all together, and yeah, it looks quite different. And then this is a little video of how it looks as well. So hopefully that's playing for you now. I'll let it go through a couple of times in case there's any lag. But so the different coloured balls are the same markers that you'd see on the person. So that's what the camera sees. And the squares on the floor are the force plates, and the arrows that are coming up from the floor are the ground reaction forces, the force vectors, which shows how the person's body weight is moving through their foot and around their body as they're walking down the room. So this is the kind of thing that I'll be doing, and I'll be adding my sensor into this sort of setup on the knee to listen to the noises that are coming out of the knee and pair it with this motion capture. So we'll have some, hopefully, quite good gait movement data and hopefully some good sound data, and we can bring that together and see what it tells us. So this is one of the things I would like to do in our lab, is use the instrumented stairs. So you can see this person climbing the stairs. Hopefully, again, I'll let it run a couple of times in case there's a lag. And you can see the force vectors again coming out of the stairs as he's using them. And it shows you like how his force, how his body weight is moving through him or through his joints and stuff from the floor as he's moving. And one of the reasons I want to use stairs is when you're using the stairs, you tend to actually experience about 3 times your body weight in force through your joints. So it's quite impactful, whilst also it's something that everyone does, or lots of people do every day. So it could be quite a nice activity to see if we can hear some good noises, hopefully, from their knees. So the future work for my PhD is very much about pulling the work streams together now. So we have the patch kind of coming together, the electronics are coming together, I'm learning the motion capture. So it's bringing it all together, getting it into the lab, getting it all working, all synchronized. It will all come together beautifully, I'm hoping. Collecting some data and then processing the data. Now, this really should have started middle of last year, middle of my second year, but we've had a bit of trouble getting into the lab for mainly COVID reasons. So yeah, I've not been in since March. We're just getting back now, but we're not really allowed to recruit patients, and we're not allowed to recruit outside the university. So it's slow. I'm hoping we'll get there soon, but yeah, it's been a bit slow. So the next couple of slides are a bit of fun things I've done alongside this work. So some public engagement stuff. So in our lab, so you can see the teaching lab and the clinical lab joined up together. We hosted the first Welsh National Biomechanics Day. So we had a primary school come in and visit us, and they all got to use all of the different equipment. So they did some motion capture. They used our ultrasound machine. So they saw the Doppler on their veins in their arms. They had a really good time. So that was really good. We had a lovely day. Over the last few months where we've not been allowed to go into schools, we've done some virtual visits. So this was a little boy asking us some questions about our X-ray lab over Teams, which was really, really lovely, really good fun. And we've developed a mechanical hand activity. So you kind of use straws to represent the bones, and then there's string inside, and you can pull on the string and close it. So the string is like almost like tendons. It's not a perfect model, but it's quite a nice activity. And then I was costed in on a RA Engine Genius project to do some work alongside my PhD. And we've developed a electromagnetics badge for Girl Guiding Cymru, which is coming out in the next couple of weeks. So I'm quite excited about that. It's been a big project, but it's been really good fun, and I'm hoping that the girls will get a lot out of it. Yeah. So to wrap up, this is all I've really got, I'm afraid. The overarching aim of my study is to try and use acoustic emission, structural health monitoring technique to listen to osteoarthritis in knees and to see whether you can monitor the degradation. So if someone presents when they're 40 with an achy knee, you can then monitor them over several years and see whether they're moving towards an osteoarthritic sound, potentially. That's where it will hopefully go in the future. And will hopefully improve outcomes for people with osteoarthritis. Any questions? I'm happy to take any questions.
Paulie, thank you so much for taking us through that. I thought it was fascinating. What I'd really like to ask is kind of what have been the, obviously you said that there were limited interactions with kind of real people or real patients, but what kind of has been the reaction from people in the medical profession or from people who have arthritis that you've talked about? What's been the sort of human angle to what you've been doing?
So people with arthritis would seem to think that they'd like kind of anything to diagnose it earlier or to try and inform treatment like timescales and things like that. Clinicians, it's kind of mixed. So it very much depends on what sort of clinician you speak to. So physiotherapists tend to be quite, we don't need any help managing this. We know what we're doing. Technology isn't going to help us do this. Surgeons can be quite excited about new technology. It very much depends on the surgeon. One of the aims of one of the kind of research outcomes that I want to hit is doing a questionnaire for clinicians, and kind of going, where do you think this would fit in? Would you use this to inform treatment timescales? Would you use this to refer people to different things that might help them? So whether that might be swimming or group sessions of, like, I don't know, meeting up on a Wednesday and having a walk, or something that can kind of help people with early osteoarthritis manage their condition themselves and give them ownership over it.
Excellent, thank you.
Could I come in and ask, there seems to be an assumption that there is only one sound source here. Are there not going to be other sources of noise emanating from knee movement?
Quite possibly. We don't know yet. So what I'm looking for at the moment is osteoarthritis, because the patient cohort is quite well defined. So when you have used an X-ray or an MRI, you can group people quite nicely. So I could have a group of, say, under 30s, a group of under 40s, and then people with early stage OA and people with late stage OA, and I can learn what early and late stage sound like based on their X-ray KL grades from a radiographer, and then learn what that sounds like. I think something I would like to do, if this works, and if there's any sort of funding afterwards, would be to work with either a surgeon or a team who have access to an MRI machine, who are getting people with knee injuries through and listening to all these different noises, and then finding out what their MRI tells us is wrong with them. So whether that's a focal cartilage defect, a ACL tear, people with other ligament tears in their knees, I can never remember the proper name, but bone bruises. So there's lots of different things that it could be. And if I can access those patients at the point that they're accessing an MRI service, then hopefully I can start to understand what they sound like as well.
Polly, sorry, yes, I just had a couple of things that occurred to me. When you were talking about learning what the sounds are of the various injuries and the levels of them, that sounds very data sciencey. Is that somewhere that you're going to? Or
Hopefully if we've got enough people with enough noises from enough knees, then we'd be able to run some sort of machine learning or something that you could just listen to someone's, you could send them home with something to listen to their knees. They wear it for a day, they send the SD card or whatever back in, and you put it into a machine and it tells you what's wrong with them. One day. I feel like that's a good way away. But
the second thing was more practical. Did a little bit of sport a long time ago, and you were talking about sticking things to your skin. And I used to wrap my ankles with zinc oxide tape, and that's very sticky and very forgiving to skin. I don't know if that's something you've looked at.
Yep. So the sensor needs to be coupled to the skin itself, so there's no air gaps in between, and then we can put something over the top. So zinc oxide tape is good. We often use cohesive bandage, so it sticks to itself, because that's kind of nice and stretchy and also quite forgiving and doesn't leave any sticky residue on the skin. Because if we're dealing with people who are quite elderly, it can, like, even some sticking tapes can pull skin off and cause tears in skin, so we have to be quite careful. But yes, zinc oxide tape is great.
Thank you.
Yep. So we use it to look at if their force vectors are normal. So when you have someone with osteoarthritis, they tend to not flex or extend their knee normally. So when you're walking, you can see how you move your body weight through your knee in a particular way, and when you have someone with a pathology, they do it differently. I think it can be used for other things. My research group mostly do knees, so that's the only thing I can really talk about with confidence, but I'm sure it has been. I just don't know.
Hi, Polly. What's the sort of frequency content of noises that come from these fractures or defects in the bones?
It varies. So most of them are around sort of the 150 kilohertz sort of range. And then I don't know if you've heard a knee with osteoarthritis, or maybe a gran or a mum or somebody. Their knees can really grate quite loudly, and it's called crepitus. So as we move towards people who have more unhealthy knees, it tends to get more towards the audible end of things and also be more frequent. But it kind of varies at the moment.
And one more small thing. I've seen you using a TNC 3.6 in your current. Have you used 4.1 that's released fairly recently?
Yeah, it has come up fairly recently. I've just got 3.6s at the moment. So yes, if it's better and can sample faster, then potentially. If it samples in exactly the same way a 3.6 does, I don't know if there'd be much point. But I don't know.
No, fair enough. I thought I'd just make you aware, because I know a lot of people are using 3.6s and don't know that the 4 series have come out now.
Yeah, no, they are good. I love the forums. I spend a lot of time reading stuff just because other people are doing interesting things. Thank you very much. If anyone if anyone thinks of any questions after, I'm happy to have emails and stuff. That's fine. So if I put my email in the thing, that's.
And just to echo what Steve said, absolutely fascinating. Thank you for sharing that. And also, if you come across any challenges or problems that you think, well, actually, if I put this out to the Whitworth Scholarship, network, the Whitworth Society, and maybe that we can help, crowdsource a solution or have some ideas or thoughts, feel free to reach out to the network. We're here to help.
Cool. Thank you very much.
Thank you.
Cool. Thanks very much, everyone. Catch you later.
Yeah, see you everyone. Bye bye.
Cheers. Bye.